Hi folks, welcome to a calculus review. Today we're going to have a few focal points taken from questions and problems that we've been having. And so we're going to focus first on derivatives because that's kind of the backbone of what we're doing here. So we have to make sure we have derivatives down. If we don't, there's no reason to proceed, basically. So we're going to start with derivatives. Then we're going to get in after we have some of the different examples of derivatives down. Move into applications of derivatives, and then we'll start to look at, in particular with the applications, related rates, L'Hopital's rule, trying to apply that, look at the mean value theorem, and then we'll finish with something might be a little bit new to you, talking about critical points and increasing, decreasing intervals. So that's what we have on tap for today. So we'll take a look and we'll go ahead and get started right now. So without further ado, say we have the derivative of x squared minus 9, that quantity raised to the 11th power, and then times tangent of x. How do we take this derivative? So the first thing we do is to notice that this is a product of two functions. So sometimes people make mistakes to this. So we need to use that product rule. So once again it becomes the derivative of x squared minus 9 raised to the 11th power, and then times tangent of x, plus is how the product rule works, and then we write that first term, so x squared minus 9 raised to the 11th, and then times the derivative of the tangent x. Okay, some people just hop right into it. I'm just trying to show that intermediate step. Now, where do we go from here? Well, if we take a look, the next place that we can go to is just taking our derivatives. And when you look at this, this is a chain rule is what's going on with this piece. So you have an 11 is the 11th power is the outer function essentially. So we can use that power rule. So you go 11 x squared minus 9 raised to the 10th power. But now we need to take the derivative of the inside. So that x squared minus 9, what is the derivative of that? Well, the derivative of x squared is 2x. So we're going to multiply by 2x, and the derivative of negative 9, since that's a constant, the derivative is 0, so we'll just close off that parentheses. Okay, with the second piece, plus we have x squared minus 9 raised to the 11th power, derivative of tangent of x, so that's going to be secant squared of x. Okay. And if we wanted to brush this up, it's not necessary, but we can. What can we do? Well, just combine the 2x and the 11. As I said, it's not necessary, but sometimes it looks a little prettier for some people. So, oh, I forgot one piece here. I'm glad we're brushing up. I forgot the tan x in that first piece. So you get 22x, and this is the nice part about brushing up. You can catch some errors like that. X squared minus 9 raised to the 10th power times the tangent x, plus x squared minus 9 to the 11th times secant squared of x. Okay, and if you ever have a question, by the way, just always, there's a chat box right there, just post it right in and I'll be happy to answer those questions as they kind of trickle on in. Alright, so that's using the product rule and along with the chain rule. We see how that works. Let's try another one here. You have g of x equals natural log of x cubed plus 5, that quantity raised to the 9th power. Now what happens for a lot of people, they'll try and just go brute force and take derivatives, use a chain rule, and all said and done there. You can make your life simple just by using properties of logarithms. Notice without taking a derivative whatsoever, we can rewrite this as 9 times the natural log of x cubed plus 5. And that's essentially what we call the power rule for logarithms. Don't confuse that with like a power rule in terms of the derivative. But so bringing that exponent on down out in front, that's a legal move for us. So now, moving forward from there, where can we go? Well, we just take our derivative for g prime of x. And how does it go? Well, the constant will stay out in front. So 9 times the derivative of natural log, remember it goes 1 over what's on the inside of the natural log. So 1 over x cubed plus 5 times the derivative of the inner function here. So the derivative of x cubed plus 5. Well, the derivative of x cubed is 3x squared, and the derivative of the positive 5 is just 0. So we can close that off. And so what we're left with here is just good old 27x squared, all divided by x cubed plus 5. Okay. Now some of you might be saying, I don't want to go through it that way. I want to do it, just get the derivative the old-fashioned way without knowing properties of logarithms. And we could have done it the other way. So here's the other approach. And I just want to try and illustrate that those do become the same thing. So say we did 1 over x cubed plus 5 raised to the 9th. Now I have to use the chain rule. In the interior function, this x cubed plus 5 raised to the 9th power, we have to use the power rule because you have a 9th power on the outside of this function. And so it becomes 9 times x cubed plus 5 raised to the 8th power. And then we have to take the derivative of the interior function, so the x cubed plus 5 now we have to take the derivative of. So that would be just 3x squared, because the plus 5, that derivative is 0. And you might say, oh, this looks different. Not quite. If you notice, what happens is the 8th power, that will cross off with 8 of the 9 power, so you're left with just a 1 up here. And so this whole thing just equals 9 times 3x squared is 27x squared over x cubed plus 5. So now, not everybody simplifies all the time, but you can see that those two answers are equal. They're different approaches. I would claim that the one on the left actually happens to be the simpler format because you're just dealing with the chain rule once rather than having to use it twice. So hopefully that makes sense on that problem. Let's move forward and try some more derivatives. So this one looks nasty. It kind of freaks people out. We have these nested roots. So you have the 4th root of 3x plus the cube root of e to the x plus the square root of cosine of x. What might make this a little more comfortable for people, not necessary, but we can write this as fractional powers. So you can write this as 3x plus, we have an e to the x plus, and then we have a cosine x, and that cosine x is raised to the 1/2 power. Okay, the e to the x, you know, just that is included with that cosine x to the 1/2 power, but since you have a 3 out in front of that root, that's the 1/3 power. And then the 3x, that's a 1/4 power. Okay, so we're going to use the power rule over and over again, and we have to be somewhat careful with how the chain rule is applied here because of these plus symbols in between. And that can trip people up from time to time. So the first thing we see this exponent out here, furthest one out, so we're going to use the power rule. So 1/4 times the quantity 3x plus, and what's in the inside, e to the x plus cosine x, then we have 1/2 raised to the 1/3, and now we're to where the 1/4 was. It has to go 1/4 minus 1, which that is just -3/4 times. Now here's where it gets interesting. We start taking the derivative of the inside. Derivative of this is easy, right? The derivative of 3x is just 3. The derivative of this piece right here might be a little bit harder. And so what we need to do is look, your outside function is that 1/3, right? Raising it to the 1/3 power. So we'll need to use the power rule again and use the chain rule on top of that. So you go 1/3, and then you have e to the x, we'll write what's just on the inside, plus cosine x, and we'll put that raised to the 1/2. Now that will be raised when you subtract 1 from 1/3, you get -2/3. Okay, so we have -2/3 sitting right there. Now, what do we need to do? We need to multiply by the derivative on the inside. This is the tricky part. Most people will close off the parentheses. This 3 is not multiplied by this derivative. It's just this e to the x plus the square root of cosine x, all that raised to the -2/3, and then you have a 1/3 there. That's the only piece that's raised to this power. Or this derivative, I should say. And the derivative that we have is e to the x plus, we need to use the chain rule on this thing. So you have to use, if you notice, we have a 1/2 power, so we'll have to deal with that first. So you have 1/2 cosine x, and this becomes to 1/2 minus 1 power, which is negative 1/2. Then we have to use the chain rule one more time for that interior function of cosine x. So what is that interior function? It would be derivative of cosine is negative sine of x. Notice that is not multiplied by the e to the x. So now with that, we'll close off that piece. Then we'll close off the e to the x plus piece. And we finally have our derivative. If you want to brush it up, this is fine actually for right now, but if you really wanted to brush it up, what happens is you can, there's a few different ways to write it. Let's see here. I'll just write it as a whole bunch of multiplication for right now. And then with room constraints on what I'm writing here, I won't be able to simplify it all into one, but hopefully you can get the gist. So notice this is negative 3/4, so that's why we're going 1 over. This 4 down in that denominator tells you it's a 4th root. And then we're going to have what's on the inside, which is 3 to the x plus, we actually have a cube root of e to the x plus a square root of cosine of x. But notice I haven't accounted for, I've counted for the 4th root being that 4 in the denominator, but I need to count for that 3. And what that does is that just cubes this whole quantity. Okay, so that's that first piece. Times. And we have another quantity. You get 3 plus. Okay, well notice this is going to be negative 2/3. It's going to put all this junk down in the denominator with a 3. You have 1 over 3 times e to the x. Oops, I forgot one thing here. Forgot the cube root. So let's get that root involved. So you have cube root of e to the x plus the square root of cosine x. And all that is squared. The reason it's squared because of that 2 right there. And all of this last piece, notice not the 3, so I don't want to close off the parentheses, just this last piece is going to be multiplied by, let's make sure, the e to the x business. So you have e to the x. When you have cosine x raised to the negative 1/2, what that becomes is 1 over 2. Oh, this is plus 1 over 2 square root of cosine x. And all that's times negative sine x. Now hopefully this shows you how this stuff works a little bit. And we'll close off that parentheses, and I think we're, so that we got that one, and now we need to close off the 3 plus. Okay, so there we go. Alright, so from here you can actually do some other tinkering with it. It's not necessary, but hopefully you can see how these roots can be listed differently. If you wanted to, you could get a common denominator and try and move all this stuff underneath into one fraction. I wouldn't say it's necessary, but just something to keep in mind, that there's different formats you can have for a final answer from here. Alright, so for the next one, q of x equals arc sine of e to the x. So if you look, one thing to take note of, and let me know if you don't know what the derivative of arc sine of x is, because we can prove it too. And so if you're in a worst case scenario, you don't know how to do it come exam time, this way we can kind of solve that problem. So the derivative of arc sine of x is just 1 over the square root of 1 minus x squared. If you don't know, as I said, just let me know. We can prove it. It doesn't take too much. All you need to do is use a triangle, and you can do this all the time. So moving forward from here, if we're to take the derivative, notice that becomes 1 over the square root of 1. Well, what's replaced the x? In this case is e to the x, so we go e to the x squared. Okay, times the derivative of the inside. The derivative of e to the x is just e to the x. And so there we have our result. So this is 1 over the square root of 1 minus e to the 2x. And if you wanted to, you could take that e to the x on top and make it look something like that. Okay, so we have all those pieces in place. let's try some harder ones. This gave a lot of people trouble from what I've been seeing. If you have an x to the sine of x, so what's actually happening here? Should we use the power rule? Should we use the exponential rule? What's actually happening when we have a w of x equals x to the sine of x? How is this different? Well, notice you have variables in both the base and the exponent. So it's actually neither. You have to use what's called logarithmic differentiation. And so first things first, what we're going to do, in order to bring this exponent on down so we can work with it, we need to take a natural log of both sides. And so we take a natural log of w of x, and that should equal the natural log of x raised to the sine of x power. And what does that allow us to do? Well, that allows us to write this in a slightly different format. So we can do natural log of w of x equals sine of x times natural log of x. Okay, where do we go from here? Well, we can take derivatives of both sides, and that's what we want to do, because now we have just a general product rule on the one side. So we'll move that d dx there. That means we're going to take the derivative of this. So on the right hand side it's going to be product rule. In implicit differentiation, you got to think about what happens on the left hand side. Since we have natural log of w of x, that becomes 1 over w of x times the derivative of w of x, which is w prime of x. And that's what we're looking for. Remember, we're looking for w prime, so we'll deal with that in a minute. Equals product rule on the right hand side. So derivative of sine of x is cosine of x times the natural log of x plus, we'll write sine of x times derivative of natural log of x is 1 over x. So that's just our product rule in play. Okay, now where do we go from here? Well, we try and solve for w prime of x. W prime of x equals, in order to get rid of that, we multiply w of x on both sides. Make sure you put parentheses around the remaining pieces. So you have cosine of x, natural log of x, plus, let's just make this sine of x over x. Okay, where do we go from here? Well, what is w of x? Well, w of x, if you look in the beginning, it's x raised to the sine of x. Okay, so x raised to the sine of x, so you have cosine x times the natural log of x plus sine of x, all divided by x. Whew. All done now. What was the giveaway to use this? Well, you had a variable in the base and a variable in the exponent. That means you're going to have to use logarithmic differentiation. So keep that in mind when you're working with these things. One last one that kind of gave some people some trouble. We'll go through two different methods on this one. I'll work it the hard way, and then I'll show you how we can make our lives a lot easier second. So most people, when looking at this u of x one, they just go straight forward with brute force and say, okay, let's use our quotient rule. This is not going to be fun. So you can go secant squared of x cubed. And we got to let the derivative, or let the bottom rest because it just did some work, is what I like to say. Or you can go the low d high and then minus high d low. That works as well. So derivative of the numerator is 1, and then minus. So the second piece, we have x times the derivative of the denominator. Okay, what does that look like? Well, that's going to be derivative of secant x cubed. So the derivative of secant will be secant x cubed tangent x cubed. And then times the derivative of the interior function. Well, notice the interior function is just an x cubed. I should point actually right here just to be a little bit safer. So derivative of x cubed is 3x squared. And so if you're brushing that up, notice you can factor out a secant out of this and out of this. And notice I took it out of both terms, right? Some people just cancel it off of one. No, it has to be in both pieces in order for us to make that cancellation. So now we have, in that first case, it's going to be 1 over secant x. So all this is over secant x. So it goes 1 minus 3x squared times x, so minus 3x cubed times tangent of x cubed. And we can actually simplify this even more. I'm not saying we have to, but just keep in mind we can actually go through it and simplify it a little bit further on down. Rather than do that, I'm going to show you a much easier way. Secant of x cubed is 1 over the quantity cosine of x cubed. So an easier way to have written this is the same thing as just x times cosine of x cubed. Okay. So now if we take this route, notice it's just a product rule, and you get u prime of x equals. So we take the derivative of x, which is 1, so times cosine of x cubed. Right? And then we have plus, so x times the derivative of our cosine of x cubed. So what's that derivative? Well, it's going to be negative sine of x cubed times the derivative of the inside. So what's the derivative of the inside? Well, it's going to be times 3x squared. And you might be saying this doesn't look like it's matching, but notice this is just 1 over cosine of x. And if you wanted to brush this up, this is cosine of x cubed minus 3x cubed sine of x cubed. So when you multiply the 1 over cosine, well, when you take the reciprocal of that, multiply cosine times each term, you'll get cosine of x cubed here, and then tangent of x cubed times cosine of x cubed just equals sine of x cubed, and that's where that comes from. So a much simpler way to solve it and actually see a result we can work with a lot quicker. So that's some derivatives review. We need to know this stuff before we move forward. If we don't know how to take derivatives using chain rule, quotient rule, product rule, logarithmic differentiation, there's no reason to move forward. You need to go back and we need to study those derivatives. So now, though, if you do have that down and you feel comfortable with it, it's time to move to some applications of derivatives. And so the ones we're going to start with here are related rates. The first one we'll take a look at is this kite problem. And so the reason why this was chosen, a lot of people struggle with this on the homework. So I wanted to make sure that in terms of this related rate we get to see this problem, and then we'll work on another one that's a little bit different we haven't seen before. So we have a kite 100 feet above the ground, moves horizontally at a speed of 2 feet per second. At what rate is the angle between the string and the horizontal decreasing when 300 feet of string has been let out? Okay, so you're going to see a beautiful drawing here. This is like Picasso all over again. So here's a person, and then here's some kite up here. See, beautiful, I told you. And you can have your little streamers or whatever. So what we're doing is we know that this makes a right triangle. Okay. Things that are not changing. A kite 100 feet above the ground, and the reason why that's not changing, it moves horizontally. Okay. So you have moving horizontally, and so this is a constant 100 feet. Okay. So we have moving horizontally, so this is going to be some form of a label x because it is a variable here. Okay, so that's our horizontal distance. Now, at what rate is the angle between the string and the horizontal decreasing when 300 feet of string has been let out? So now listen to this. When we are letting out string, so notice the letting out of the string occurs right along this line where the kite is. So that is a variable because we're letting it out. So we'll label that side y. And then we're talking about an angle, and so we'll put in a theta right there. So now with all these pieces together, let's see, how can we tackle this problem? Well, so this takes some guess and check work a little bit, but the information that we do have, now that we have our drawing, some of the givens The 100 feet isn't changing, so that's already in there. We put that in the drawing. You have this moves horizontally at a speed of 2 feet per second. Okay, so what does that mean? Well, that means dx dt equals 2 feet per second. Now, why dx dt? Well, notice this is a rate because you have feet per second, so that takes care of that. That's why we have to have a dt involved. And why is it the x and not the y? Well, we're talking horizontally, and your horizontal is along that axis there. Okay, so we have that. What's another piece that we have? Well, between the string and the horizontal, at what rate is the angle between the string and the horizontal decreasing when 300 feet of string has been let out? So what we're going to plug in, not immediately, we're looking at the case when we have 300 feet of string. Or another way, easier way to say that is y equals 300 feet. Okay? What are we looking for? At what rate, so that means we're going to have a dt involved, is the angle, so that theta. So dt, and we have a theta involved, so we're looking for d theta dt. Alright, so let's think about this. We want to start to relate these things in terms of an angle theta, which is right here, and then the information that we have a dx dt, and we have a y value, right? And then we have that this is always a constant. So where are we going to go from here? Well, the easiest way for us to look at this, and you have options, right? So what most people would say is, okay, the easiest way, well, since we have this dx dt to work with, most people would say tangent of theta equals 100 over x. And that would be fine. With the exception, you're going to create a little more work for yourself that way. And what you'd have to use is a Pythagorean theorem along the way. And I'll explain why. When you take this derivative, think of what's happening. Well, this is x to the negative 1. So you're going to have to write this 100x to the negative 1. When I take the derivative, I get negative x to the negative 2 power, essentially, times this 100. And so we're running into a little bit of trouble there. That's a little bit harder to work with. An easier method, so this is option 1. So option 2 would be flip it. And the way to flip it is take cotangent of theta. Well, cotangent of theta equals x over 100. Right? Now our life's a lot easier because this is essentially cotangent of theta equals, remember this is just a constant, so a lot of people say, oh, I have to use the quotient rule. No, you don't even have to use that. That's 1 over 100 times x. Now, look, when we take a derivative, the x actually disappears, so we don't even have to do a calculation with that. We just plug in a dx dt. And so we're going to have to work with the theta, but that's okay. We can work with that. It's not going to be a big deal. Okay. Now, some of you may be saying, well, wait a second. Why didn't we do something like sine of theta, 100 over y? Or a cosecant of theta, where we go y over 100? Well, the reason why, notice we don't have a dy dt anywhere. So that's going to make it a little bit harder for us to figure it out. Just more work along the way. So the cotangent of theta is probably our best option here. And so that's what we're going to work with. So what we'll do is, working with that cotangent theta, we're going to take our derivative with respect to t of both sides. So derivative with respect to t of cotangent theta. Remember, the constant can get pulled outside of the derivative. It doesn't matter when it's multiplication. So we have d dt of just x. Okay, so what's the derivative of cotangent theta? Well, that's going to be negative cosecant squared of theta. And then times, remember we have to kind of use that implicit differentiation idea, times d theta dt. Now on the other side we have 1 over 100 times dx dt. Okay, so now looking at this, cosecant squared, remember that's 1 over sine squared. So what we could do is multiply both sides by sine squared in the negative symbol as well. So this will allow us to solve for d theta dt. And once again, if you ever get lost in a step, just let me know and I'll be happy to help kind of clear it up. So remember, we multiply by negative sine squared on both sides. That'll cancel the left hand side. So then times negative sine squared theta. Now you might say, well, wait a second. How do we know what sine squared theta is? And the answer is right in here. We have the fact that y equals 300. So y becomes 300. What's so important about that? Well, if we have that piece, we can rewrite this. We get the 1 over 100. dx dt is 2. So times 2. And then for that next component, we have sine of theta squared and a negative symbol out in front. So let me put the negative. So negative, and we have sine of theta. Well, what's sine of theta? Well, notice you have 100 here and you have 300 there. Okay, so 100 is your opposite, 300 is your hypotenuse. So that's 100 over 300. Be careful, that's the part we're squaring. Okay. If you want to brush this up, you can. It's not really that necessary, but notice this 100 down below will cross off with that 100 up above. And so what we'll get is, I'll try and fit it in here. We'll see if we can make it work. So you'll have 2 times 100 over 300 squared. And I forgot one little thing, that negative symbol right there. And this should be in terms of what? What is our label? Well, it's angle, so we're talking radians. And then it's per second. And the reason why we know it's per second, because you have a second right there. And that's one thing we kind of lucked out in terms of all our units being in seconds in this case. That doesn't always work out that way. So, and yeah, you can, if you need to, you plug it in a calculator, but just leave your answer like that. That's fine. Oh yeah, we can always brush this up even more. So cancel off 2 zeros of the 100 with you'd have a 300 times 3 on the bottom. So yeah, actually we might as well. D theta dt equals, notice the 100 would cancel off with one of the 300, so we'd have negative 2 over 3 times 300, and this is radians per second, and that should equal, well, notice that would become 150 down below, so it should be negative 1 over 450, I believe, radians per second, if I've done the arithmetic right. So now notice actually though it asks for decreasing, so the negative is telling us it's decreasing, and so decreasing at a rate of what would be 1 over 450 radians per second. Okay, hopefully that makes sense. Related rates, I know word problems can freak some people out. Don't let it. I mean, all we did is just set up a diagram and then kind of worked with it and see what variables we had to work with. Okay, this next one, this is going to be a challenging one coming up, so you might not have seen this one yet. We have the sun rises at 6 a.m. and sets at 6 p.m. and goes directly overhead. You are standing in the shadow of a mountain, and notice the shadow of the mountain is decreasing at 2 feet per second at 10 a.m. How high is the mountain? So to do this one, kind of illustrate it, I'll just have the mountain. You can have it start up and then go up, but at the end of the day, I have a mountain and then I have some drop off here, right? And someone's standing in the shadow. Okay, and then you have the sun kind of passing. And remember, it goes directly overhead and then comes back down. But what's happening is the sun is going over that mountain, and this dark line right here represents our shadow. So it doesn't seem like we have much. The only thing we have is the shadow of the mountain is decreasing at 2 feet per second. So that tells us the shadow, which we'll call x, is this distance right here. We'll need to work with that. Okay. Well, what else do we have? Well, we want to try and find how high is the mountain. So in this case, we'll just label this h. Remember, though, is the mountain's height changing? Not whatsoever. So this h is just a constant. So that's something to keep in mind. Now, the other big component here. It doesn't seem like we have any other information, but we do. The sun rises at 6 a.m. and sets at 6 p.m. So this is a 12-hour time span. Okay. Think about what happens. So your sun, sorry for not having it here, but it goes up, and we'll have the sun in different periods of the day. And then all of a sudden it sets off on the horizon. Okay. Think about the different angles that we go through here. So at this point, we're making some angle down below, right here, and we'll call this theta. Okay, and that's what's happening with the sun corresponding to the times throughout the day. Now, with that in mind, we can look at our givens. We actually have some given information. The given information that's easy for us is the dx dt. It says decreasing, which means negative, at a rate of negative 2 feet per second. And this is at 10 a.m. I'm going to emphasize that in a minute. Okay. The other given that you might not see necessarily is if the sun rises at 6 a.m. and sets at 6 p.m. Notice we started on horizon, we finish on horizon. How many degrees do we go through? Well, that's 180 degrees, which in terms of radians, that's pi radians. So this is pi, but now how many hours do we have involved? It took us 12 hours to go pi units, so pi over 12 radians per hour. I want to draw your attention to this though. Notice one of these units is hours, one of these units is seconds. So when we're actually doing our work, we're going to either have to convert all the seconds to hours or hours to seconds. Doesn't really matter which one, but at the end of the day we're going to have to do that. So I would say though, easier route would be to convert this into seconds, and so we can do that pretty easily. So we just kind of set up a chain here. There's 1 hour is equal to 60 minutes, and then times another 1 minute gives us 60 seconds. So notice another way to write d theta dt. 60 times 60 is 3,600. So we have pi times 12 times 3,600, and then that's radians per hour. Okay. Alright, so now we're ready to kind of set up an equation and see what we can do. There's one extra component that we haven't really used yet. Is this at 10 a.m.? Well, think of it this way. At 10 a.m., if we're starting at 0 and we're moving on up, in pi over 12 radians per hour, if we start at 6 a.m., so right here is 6 a.m. (7 a.m.) would be pi over 12. So notice I have it kind of behind the mountain here, but you can pretend it's way off in the distance. But this angle, so this angle right here, should be pi over 12. If you move to 8 a.m., you'd add another pi over 12. If you move to 9 a.m., you'd add another pi over 12. So what we have after a while, so at 10 a.m., what we know is theta equals, we've gone 4 hours times pi over 12 radians per hour. So that should be pi over 3 radians. And notice that is a variable. That's changing throughout the day. So that just occurs at the 10 a.m. time slot. We have pi over 3 happen to be our radians. So now what we're ready to do is set up an equation, and notice we have two sides here. H, if you recall, once again, H is the constant. So keep that in mind when we're taking derivatives here. So having that as a constant, that'll be a big component as to what's going on here. So you have options, once again. Option 1, the obvious one, tangent theta. So tangent theta equals h divided by x. But notice, once again, our variable, which we'll have to take a derivative of, we'd have to get a negative x squared. So that's going to be a harder route for us. Option 2. Notice, in this case, we can write cotangent of theta, once again, equals x over h. And now we're rocking and rolling because h is a constant. In fact, it might benefit us to write this as h times cotangent of theta. Okay, because h is that constant, so you multiply both sides by h, and you get h times cotangent of theta equals x. That seems like the winner chicken dinner right there. So let's take our derivative of that nice little function. So you get d dt of h, oh, we'll pull the h on out because that's a constant, times cotangent of theta times the derivative with respect to t of x. Okay, so this becomes h. What's the derivative of cotangent theta? We just talked about that, so I just want us to see an extra example where we have some options. Negative cosecant squared of theta times d theta dt. And on the right hand side is just dx dt. Okay. We know some values, right? And we can actually solve for h right away by multiplying once again by negative sign squared on both sides, because cosecant squared is 1 over sine squared once again. So you have h equals, oh, and we can divide by the d theta dt as well. So you have dx dt over d theta dt times sine squared theta. Oh, and a negative symbol there too. Okay, so the key piece that we're going to use here, remember we aren't allowed to use calculators in our calc class here. So when we take a look at this, what is theta? Well, we know theta is pi over 3. So if theta is pi over 3, that's a special triangle that we need to know. And that means that that's a 60-degree angle, that means this is a 30-degree angle, or pi over 6 radians. That might benefit you a little bit if this is the right triangle. So that means this is a square root of 3. This is a 1 right here, and this is a 2. And so now we're ready to tackle this problem. So we have dx dt. What is dx dt? Well, if you look, it's negative 2 feet per second. So we have negative 2 divided by, well, we're dividing by this pi over, oh, and I wrote up here radians per hour. My apologies, this radians per second is what we converted to. That's pi over 12 times 3600. Okay. And then where do we go from here? Well, we got to square sine of theta and have a negative symbol out in front of that. So negative, and sine of theta is square root of 3 over 2. So square root of 3 over 2, that quantity squared. Okay. So what does h equal? Let's see here. We can bring the 12 and the 3600 on up. Notice the negative and negatives make positive. this 3 over 2 becomes just square root of 3 over 2 squared becomes 3 over 4. So this 4 and this 2 will cancel and leave a 2 down below. And so we'll have 12 times 3600 times, what do we have here? So this will be, we have a 3 and a 2. 3 here, 2 here, pi there. And I think we're in business today. Just double checking the arithmetic there, making sure we cancel things off correctly. So yeah, that should be pretty good to go. And so now where do we go from here? Well, we can cancel this off. That would make 6 up top. And what else do we have? I think that's pretty good. So 6, so 18 times 3600 divided by pi. And so whatever that comes out to be, and what is our answer represented in terms of? Well, when you think about it, we've been talking about feet per second. So this should be in terms of feet. Okay. So hopefully that makes sense on how that works out. Seeing how the cotangent of thetas and all that jazz comes together once again, along with d theta dt, dx dt, and setting this up. The reason why I like this problem a lot, just because of the fact you look at, we have the sun rising at 6 a.m. and setting at 6 p.m. That doesn't really seem to tell us much. And the only thing that seems like a rate here is this 2 feet per second. But you can break down this problem and actually solve for how high a mountain is. And it doesn't have to just be an example here. I mean, you can take this and start to get estimates to scale here. So it gives you an idea of the power of calculus. That's why it's kind of a nice problem. Alright, moving on to another application of derivatives. For what values of a and b is the following equation true? And so we have this limit as x approaches 0 of sine of 2x plus a plus b over x squared equals 0. So when we're taking a look at this piece, we have a couple different ways to approach it. One thing that people like to do, notice as is, if you plug it in, you get 0 over 0 and then you get b over 0. So you need this to be defined, otherwise we're going to run into problems. So we have an approach that might make our lives a little easier. We can get a common denominator for all the terms. It's not necessary to do it this way, but this is one of the routes. And so if we do, we already have the common denominator in the first term. So you get sine of 2x. If you want to make this a as a over something, a times something over x cubed, notice if we put an x cubed down below, we need an x cubed up above. So that means we need an ax cubed here. Okay. Well, with that in mind, let's see what's the missing piece. Well, x squared times x gives us x cubed, so we need to multiply both the denominator and numerator times x in that last term, so plus b times x. And we want to make this equal to 0. Okay. Well, in order for this to occur, when you look at this summation here, we need to use L'Hopital's rule. Right? Because essentially what we have, when we plug in across the way, you get 0, 0, 0, 0. Right? So this is 0 over 0. So what we'll do is we'll use L'Hopital's rule, and I'll shorten that by L'Hop. Okay, so we have limit as x approaches 0. What happens? So we get in the denominator, that should be the easy term. So L'Hopital's rule says take the derivative of the denominator and numerator separately. So the derivative of the numerator, what do we have? Derivative of sine of 2x is just going to be 2 times derivative of sine is cosine, so cosine 2x. I kind of did that out of order for those of you that didn't recognize that. So you go derivative of sine is cosine 2x, and then you take the derivative of the inside, that's where the 2 came from. Next, a is a constant. X cubed is where we're taking our derivative. So notice that becomes 3x squared, right, because you bring that down with the power rule. So we can write this as 3 times a times x squared. And then we have plus derivative of b times x is just going to be b is the constant there, so you have b. Alright, where do we go from here? Well, what that means, notice when we plug in, we would get 0 in the denominator. So you get 0 in the denominator. In order for this limit to exist and be equal to 0, if we have some non-zero number up top, we've run into problems. So in order for this to work, we need the numerator to equal 0. So we need 2 cosine of 2x plus 3, oh, I wrote 2x. I should be careful there. Notice what number we're going to be plugging in. 2 times 0 plus 3 times a times 0 squared plus b equal to 0. Because if it doesn't equal 0, notice the limit does not exist, and we need that limit to equal 0 altogether. So you need a 0 over 0 scenario. So notice this part, the 3 times a times 0 squared, that's a 0. Okay. 2 times cosine of 0. Well, cosine of 0 is just 1, so you get 2. So you get 2 plus b equals 0. Well, notice right away we have b equals -2. Okay, and actually at this point, if we had taken a different route, we could actually solve for a right away as well. But we'll kind of continue through this method. A lot of people kind of like this method, so from what I've gotten on feedback. So we'll kind of stick with this. This works the best for that case. So now, where do we go from here? Well, we have what b is, so that tells us that we can replug this in now. We got limit as x approaches 0 of 2 cosine of 2x plus 3 ax squared minus 2 all over 3x squared. Now notice what happens. We need this to equal 0, and luckily this gives us a 0 over 0, so that means we can use L'Hopital's rule again. So we have the limit as x approaches 0. Notice we're taking our derivative with respect to x, so the denominator should be the easier part. So you have 3 times the derivative of x squared is just 2x, so 3 times 2x would be 6x. And the derivative of the numerator, notice when we take the derivative of cosine, that's going to be negative sine of 2x. And then times 2, and that will multiply by this 2, so you get negative 4 sine of 2x. Plus derivative of our 3ax squared, notice you bring that 2 on down, you get 6ax. Okay, and once again we need this limit to be equal to 0. In order for that to happen, what must occur? Well, we need another scenario, and luckily we plug in 0. You get 0 in the numerator because sine of 0 is 0, and 6a times 0 is 0, and then the denominator is 0, so you have another 0 over 0. So this whole thing, we can use L'Hopital's rule one more time, and hopefully this will be the big ticket. If you look down below, we get 6. What's happening up above? Well, you get negative 4. It will be the constant out in front. Derivative of sine of 2x. We've already kind of talked about that right from the get-go. That's going to be 2 cosine 2x. So we multiply that 2 times negative 4 gives us negative 8 cosine of 2x. And then 6a times x. So notice that's plus the 6a. And this whole thing, recall, it needs to equal 0. Now we're ready to plug in 0. So notice when we take this, well, we'll worry about the 6 in a second. So we take this, we have negative 8 plus 6a. So we get negative 8 plus 6a. We plug that in because cosine of 0 is 1. And all this over 6 equals 0. What does that mean? Multiply both sides by 6, and the denominator goes away, and you're still left with 0 on the right hand side. So negative 8, oops, not a, negative 8 plus 6a equals 0. So that means when we move the a on over, or move the 8 on over, you get 6a equals 8, which means a equals 8 over 6, which is the same thing as 4/3. Right? So in this case, we have a equals 4/3, and b equals -2. And there's our final answer. Okay. Hopefully that makes sense on that one. If you have any more questions on that part, just let me know. Alright, let's move forward, try another L'Hopital's rule problem. Okay, so this one, how do we actually solve this? Well, there's a couple different ways. Notice we have, though, when we plug in infinity, you get infinity here, and then you get 0 up top, infinity to 0. What the heck does that mean? Well, what it means is we need to do some work here. In order for us to do some work, we need to do some properties of e's and natural logs. Remember, e and natural logs are inverses of each other. And I'll move the limit, actually. We'll start with the limit as t approaches infinity, because I can move limits anywhere the continuous function exists. So we'll move that, and then we'll have natural log of 4 to the t plus 7 to the t over 5 raised to the 1 over t power. And so what does that allow us to do? Well, it allows us to pull the 1 over t out in front. So this thing is the same thing as e to the limit as t approaches infinity of 1 over t times the natural log of 4 to the t plus 7 to the t divided by 5. Okay. And we have a couple options here to make our derivative a little bit easier in a second. Let's do this. E to the limit as t approaches infinity. It goes 1 over t times. We can break this up into two separate natural logs. So you can go natural log of 4 to the t plus 7 to the t, and then minus natural log of 5. And why is that important? Well, notice that minus allows us to separate this into two separate e problems where we have e involved. So you can go e to the limit, and we'll worry about the first term. T approaches infinity. Now we'll combine that 1 over t here, so you get natural log of 4 to the t plus 7 to the t all over t. And in the second case, though, we have minus, and I'll move the limit over there. Remember, we have continuous functions, and across terms we can move our limits, so we have natural log of 5 over t. All this is up in the exponent, by the way. So notice, though, this whole part, as t goes to infinity, that thing's going to 0. So nothing to worry about there. We're done on that piece. So now this is the bugger that we got to look at. But we have 0 over 0, right? Or not 0 over 0, sorry. Infinity over infinity. That is an indeterminate form. So if that's the case, we can use L'Hopital's rule. And I'll put L'Hop for L'Hopital's rule. And you have the e raised to the power of the limit as t approaches infinity. The bottom part should be the easier of the two. So you have 1 down below. In the numerator, though, that might be a little bit of a tricky one. So we have 4 to the t plus 7 to the t. That's the derivative. Now we need to do, if you take a look at what happens here, we need to use our, what am I going to say? Chain rule, sorry. And so this means we have to use 4 to the t natural log of 4 plus 7 to the t natural log of 7. Okay. So now you might think we need to just continue to use L'Hopital's rule again and again and again and again. Actually, no. So this is where understanding some of the limit rules that you have before and all that jazz, it can come in play and come in handy big time. So you have a 4 to the t natural log of 4 plus 7 to the t natural log of 7, 4 to the t plus 7 to the t. So with this in mind, what we'll do is we'll try and make this so we can simplify this a little bit. Notice the higher of these two values with our base is the 7 to the t. So what we'll do is we'll try and take a 1 over 7 to the t, but I can't just do that. and multiply willy-nilly. If I do it on top, I have to do it down below. So if I take that and the 1 over 7 to the t down below, what that allows us to do is, since the t powers are the same, we can rewrite this. So you get e to the limit as t approaches infinity. So multiply the 4 to the t natural log of 4 times 1 over 7 to the t. Notice you get 4 to the t over 7 to the t natural log of 4 plus 7 to the t, and the 7t will cancel. You'll be left with a natural log of 7 there. In the bottom case, you're left with 4 to the t over 7 to the t, and then plus a 1. Just to simplify this a little bit further so you might be able to see it a little bit easier, this is e to the limit as t approaches infinity. Now we have the first term is 4/7 raised to the t times natural log of 4 plus the natural log of 7 all over 4/7 raised to the t plus 1. As t goes to infinity, let's see what happens. Now, some people might struggle when we're taking a fraction and we square it, then we cube it, then we 4th power, 5th power, so on and so forth. But when you start to think about what the graphs of these things do, right? This is the graph of y equals b to the x, where b is greater than 1. If you take a look at the other graph, it's not supposed to touch there, but hopefully you get the gist. This is the graph of y equals b to the x, where b lies between 0 and 1. 4/7 lies between 0 and 1. And the way to see that, I mean, just try 1/2, for example. If I take 1/2 and I square it, I get 1/4. If I take 1/2 and I cube it, I get 1/8. What am I doing? I'm getting smaller and smaller numbers that are getting closer and closer to 0. So this whole thing right here goes to 0. And this whole thing goes to 0. So what we're left with is e, and then 0 times natural log of 4 disappears, but so we have natural log of 7 up top, and 1 down below. That's just e to the natural log of 7, and notice that it just gives us, when you go e to the natural log of 7, the e's and natural logs, the way you can think of that is just canceling, and so we're left with just an answer of 7. And that's our final answer. Alright, so we've seen L'Hopital's rule. Let's try one more, and this is once again the logarithmic type of idea. So notice we have a problem right now. We have infinity raised to essentially this natural log of 2 over infinity goes to 0. So the way we can approach that one, you can do an e to the natural log, and so e to the limit as x approaches infinity. Oh, by the way, if you want to do, you can set y equal, and then you take a natural log of both sides. It's doing the same thing. So that's another approach you can take as well. So, but in this case, e to the limit as x approaches infinity, we said natural log is what we'll do with this. So natural log of x to the natural log of 2 over 7 plus ln of x. Okay, and what that allows us to do, once again, is bring that exponent on down. So we get e to the limit as x approaches infinity. And I'll actually do a couple things at once here, and if you struggle with seeing it, just let me know. We can bring the natural log of 2 and then over 7 plus natural log of x. Natural log of 2 is just a constant, so we'll leave that right there for now. But so you have a natural log of x, and when we brought this exponent on down, notice the 7 plus natural log of x, it can naturally, even though it was originally underneath the natural log of 2, you can move that to whatever bottom of the fraction you want. So we'll move it this way. And the reason why is what we've done is we've set up where we can use L'Hopital's rule. So you can pull the e to the natural log of 2 out in front of the limit. And so you get limit as x approaches infinity. Oops, infinity. And it has a mind of its own sometimes. Natural log of x over 7 plus natural log of x. And so notice when we plug this in, you get infinity over infinity. Okay, so what do? Well, this becomes e, by using L'Hopital's rule, e to the natural log of 2, which we could actually simplify that if we wanted to at this point, but it's not necessary if we want to wait till the end. Till the limit as x approaches infinity, the derivative of the numerator is just 1 over x. The derivative of the denominator is 0 plus 1 over x. So, I don't know much, but I know when we take that limit, you get e to the natural log of 2 times 1. And e to the natural log of 2, we already discussed how these two things kind of cancel each other out, and you're left with a good old answer of 2. Okay. Hopefully that makes sense on that problem. And so we're good to go there. Now, before we go any further, the next piece we're going to take a look at is the mean value theorem. So the mean value theorem, what do we have to have? So our given, we need a couple things. We need a continuous function, f on a closed interval. AB. Okay, and so let's say we have some sort of drawing. Here's A, here's B. In order for it to be continuous, we can have all sorts of funny business go on here. But you have some point when it hits B, some point when it hits A. And what we're saying is we can draw, oh, do not let your eyes fool you, that is a straight line. I'm drawing a straight secant line there. How do we figure out the slope of that line? If this is f of x, that means that this point right here is f of b, and this point, when we take a on up and cross it over, that has to be f of a. So when we take a look at the slope of this secant line, or this average rate of change from A to B, the way to calculate that, you subtract the y values and you divide by the difference in the x values. And yes, for the last one, all that work for 2, yes, it does come out that way. A lot of those problems, when you actually take a look, we'll work them out and it'll come out to a simple number. As I mentioned before, we don't need a calculator. You haven't seen me touch a calculator yet, by the way. So if you actually work them all out, you'll get some simple answers sometimes. And if it's nasty, you just leave it as a nasty answer too. If we aren't working with calculators, it's fine. We can always punch it in. I mean, you can train pretty much anyone to punch in a bunch of numbers. So yeah, in terms of back to this mean value theorem, what is actually happening here? Well, when we take a look at this, we have this f of b minus f of a all over b minus a. That's the slope of the secant line. What the mean value theorem states is our conclusion. There exists a C in, oops, let me make this the open interval, in AB such that the derivative at that point C is the same as the slope of that secant line. Okay, that's all we're saying here. Now if I look at this graph, this looks all sorts of funky. There might be more than one, by the way. But so that's slope of that line, and I want to draw a tangent line, and we'll call that point right here C, maybe. Trying to draw a straight line with this pen and it's not quite working there. So what's happening, I'm not saying that's the exact point, but maybe on this curve it's something like this. There's your tangent line that actually has the same slope as that secant line. That's what the mean value theorem is stating. That's what we're trying to get across. So if you have some average rate of change, sooner or later, over an interval, sooner or later at some point you were going at that that rate. This is actually useful. Say you had an average velocity over a time period. You can actually say, well, at some point you were traveling at that velocity during the time, as long as you weren't all of a sudden transported. It's not like Star Trek or anything. So, but you can make guarantees in those ways, right? That's what the mean value theorem is stating to us. So now let's see a problem that a lot of us had questions on. Suppose f is a differentiable function such that f prime of x is less than or equal to 3 for all x in this interval -1, 6. Okay? Oh, that just means is an element of that closed interval -1, 6. If f of -1 equals 4, the mean value theorem says that f of 6 is less than or equal to v for what value of v? Choose v as small as possible. Okay, so what does the mean value theorem state? Well, that just states that we have, remember, it's the f prime of c equals f of b minus f of a all over b minus a. Right? That's what we just talked about. So if that's the case, what do we have? Well, our interval is just -1 and 6, so let's plug that in. We have f prime of c equals, well, we have, we'll start with the larger value. That's just kind of a natural thing to do here when we subtract. Not necessary, but as long as we're consistent. If we start with f of 6, that means we need 6 down below, so 6 minus -1. So notice we have f prime of c, oops, equals, well, f of 6, we're trying to look for that, so we'll leave that as is. F of -1, what is that? Well, it's 4, so we'll go f of 6 minus 4, and all over 7. Right? Now, where do we go from here? Well, we have a piece of information, and it's f prime of x is always less than or equal to 3. So that means c is just some x within this interval. Right? We know that from the mean value theorem. So this thing must always be smaller than or equal to 3. So in that case, we can have a new inequality. We have 3 is greater than or equal to f of 6 minus 4 all divided by 7. Okay, so how do we solve this inequality? Well, just multiply both sides by 7, so we get 21 is greater than or equal to f of 6 minus 4. Now add 4 to both sides, and you get f of 6 is less than or equal to 25. So what does that mean for v? Well, it means v, the smallest possible. That is the smallest possible value. Okay, hopefully that makes sense on how the mean value theorem works. That's what we're kind of trying to work with here. And so we can see another one where we actually try and solve some things with the mean value theorem. So find all numbers c that satisfy the conclusion of the mean value theorem for the function f of x equals e to the -3x on the interval 0, 9. Okay, so we have that closed interval. Well, what are we looking for? We're looking for f prime of c equal to, and we have that interval 0, 9, so it goes f of 9 minus f of 0 all over 9 minus 0. Okay, so we'll do a little side work over here, and then we'll start worrying about solving the problem. So if we go f of 9, what do we get? Well, we get e to the -3 times 9, which is equal to e to the -27th power. F of 0, notice that becomes e to the -3 times 0, which e to the 0, that's always going to equal 1. Okay. The other piece that we're going to need is f prime of x. We need to figure out what that is so we can get f prime of c and solve for that c value. So we have the derivative of e to the -3x. Notice you write down the e to the -3x, and then multiply by the derivative of the material up in that exponent. So that's times our -3. So another way for us to write that, f prime of x equals -3e to the -3x, and that means f prime of c equals -3e to the -3c. Okay. Now, moving forward from there, so we have -3e to the -3c equals, what do we have? F of 9 is e to the negative 27 minus, in this case 1 is f of 0 all over 9. We want to solve for c. Well, we talked about how to bring that stuff down. We're going to need to use the natural log, but we can't use it yet because we have that negative 3 sitting right out there. So what we'll do first is divide both sides by negative 3. So we get e to the negative 3c equals e to the negative 27 minus 1. When you divide by negative 3, 9, that it goes in there with the 9 in the denominator, so this becomes negative 27 down in the denominator. And you might be concerned because when we take a natural log of both sides, you need a positive number, right? A non-zero number, and it must be positive in order to take a natural log of both sides. Well, if that's the case, we might be concerned, but e to the negative 27, remember that's 1 over e to the 27th power, and then minus 1, so that 1 over e to the 27th is some number between 0 and 1, then you subtract 1, you're good there. Another way we could write this is 1 minus e to the 27th, 1 minus e to the negative 27th, and then all over positive 27. That's just multiplying this negative, multiply negative 1 on the numerator and denominator. That'll fix that. But it's not necessary really. All we're really concerned about is this answer where we're getting at. And so our next step is just take a natural log of both sides. And so we have natural log of e to the negative 3c equals natural log of e to the negative 27 minus 1 all over negative 27. Remember, we have a natural log and an e, so they kind of go away with each other there. So we have negative 3c equals natural log of e to the negative 27 minus 1 all over negative 27. Okay, and so now we just, to solve for c equals, we have, it's not going to be pretty. We have e to the negative 27 minus 1 all over negative 27, but then we take all that and divide by negative 3, and there's our final answer. So we got a final answer, it works out just fine, and we are good to go. Okay, looks scary, I know, but we can solve it, whether it's an e or whatever it is. That's all just algebra the rest of the way. The hardest part in terms of the calculus side of things was just getting the derivative and setting up this equation. And that's all the mean value theorem is asking us to do in those certain time frames. So where are we heading? Well, so we're going to be talking about increasing, decreasing intervals. I want to kind of touch on that real quick. And so you have these things called critical points. So when is this occurring? A critical point is when f prime of x equals 0 or f prime of x does not exist. Okay, so in order to look at this one, we're going to take a derivative and see what happens. So we get f prime of x equals, notice this is raised to the 1/3 power, so we'll have to use the chain rule. So you get 1/3 x cubed minus 3x raised to, when you do that, you have to subtract the 1/3 power, or subtract 1 from the 1/3 power, and you get negative 2/3, and times the derivative of the inside. So this is 3x squared minus 3 is the derivative of the inside there. Before, you could probably get away without having to simplify. Now though, we have to start simplifying a little bit more. And so what does this mean? Well, we have, notice down below you have a 3, you have a cube root of x cubed minus 3x, and then this means squared. And this becomes a 3, notice you can factor that out. So 3, if you factor that out, you're left with an x squared minus 1. Making our life a little easier now for down the road. So f prime of x equals, the 3's cancel. X squared minus 1, that can factor. That can factor to x minus 1, x plus 1. Okay. And then we have a cube root down below. And this can factor. We can factor out an x. And we're left with an x squared minus a 3. And then we need to square that whole quantity. Okay. So looking at this, we first want to find all the critical points. So when does this thing equal 0? Well, notice you're looking when f prime of x equals 0, so that means this thing over on the right has to equal 0. So the way that equals 0, or does not exist, so we'll start with f prime of x equals 0. That would be when the numerator equals 0. So you get when 0 equals x minus 1, x plus 1. Notice that is x equals 1 and negative 1. Okay? Oops. F prime of x does not exist now. Where do we go from here? Well, we're setting the denominator equal to 0. Now, by the way, with the denominator equaling 0, well, doesn't exist when. For the denominator to equal 0, what do we need to look at? Well, the cube root, that's not going to have an effect on this thing equal 0. Neither is a square. So we're just setting 0 equal to the terms in the denominator. So 0 equals x times x squared minus 3. So from that, you get two parts. You get x equals 0, or x squared minus 3 equals 0. Which means in the second piece, you can have x squared equals 3, and that means x equals plus or minus the square root of 3. Okay? Well, if we're taking a look at this now, we have x equals plus or minus the square root of 3. We have x equals 0. Our solutions for this is x equals negative square root of 3, 0, and positive square root of 3. Alright. So our critical points are x equals, well, notice we had 1 and negative 1, and we have negative root 3 and 0 and root 3. And so to write those in increasing order, we start with negative root 3, that's the smallest of the bunch, and negative 1. And if you're struggling, you might not say you know what negative root 3 is without a calculator. Well, a way to think of that is just keep in mind that with the root 3, if you do a square root of 4, that would be 2. And if you do square root 1, that would be 1. So this lies in between 1 and 4, so it has to be some number between 1 and 2. And that'll do the trick for us. So then we'll go 0, we need 1, and then we need positive square root of 3. Now, there's different ways to do this for the next part. Determine all intervals when this is decreasing. Some people make a sign chart or table. The way I like to do it personally is I break up a number line. And what do I mean by breaking up a number line? See all those critical points right there? We're going to mark them on a number line. And so we have negative root 3. We have negative 1. We have 0. We have 1. And we have root 3. I'm not saying this is to scale on the number line, but this will get us the gist of what's going on here. And these are your x values. And up top we're going to have f prime of x. What is the derivatives? Well, we know that those values, f prime of x equals 0. That's why you see me marking zeros right up above. When does it mean that a function is decreasing? Well, function is decreasing when you think of the slope of the tangent line. What should happen when it's decreasing? Well, the slope of the tangent line is negative. So all we care about are these different intervals, and we're going to see if f prime of x is negative. So to give you an idea of the intervals, the first interval, we go from negative infinity to negative square root of 3. Right? That's our first breaking point from here to here. Our next breaking point would be negative square root of 3 to negative 1. Then we can break it up again at negative 1 to 0, 0 to 1, 1 to square root of 3, and then square root of 3 to infinity. Okay. all we need to do is pick a value in each interval, plug it into the derivative, and see if it's positive or negative. And so I'm going to write down, just to give us a little bit more room here, what is that derivative? So f prime of x equals, it goes x minus 1, x plus 1, and then we have a cube root of x times x squared minus 3. Alright, so this might look intimidating at first, but it's not too bad because all we're worried about is positives or negatives. Now, let's pick a number in this interval. So starting from our left-hand interval, that negative infinity to negative square root of 3, pick a number in there. Well, notice that's like negative square root of 3, we said between negative 1 and 2. Let's just be positive that we're outside of there. So let's pick negative 10. Didn't have to choose negative 10. I could have chosen negative 2. I could have chosen negative 1,000,000. Does not matter. All we care about is when we choose an element from here, is it positive or negative? Well, notice, oh, and I forgot one thing on the derivative, the very important part. Notice that denominator is squared. What happens when we square a negative number? It turns positive. If we square a positive number, it's positive. So it does not matter what number we're plugging in, the denominator is positive. So we really, in this case, don't even have to check it. We just need to check the numerator. Well, notice in the first case, if we plug in negative 10, negative 10 minus 1 is negative 11, so that's a negative value. All I care is that it's negative. Negative 10 plus 1 is negative 9, which is also a negative value. If I multiply a negative and a negative, notice that makes it positive. And so I'm going to put a plus right there. What that tells me, right out the gate, is that on this interval from negative infinity to negative root 3, this function, if f prime of x is negative, remember it's decreasing, so since it's positive, that means it is increasing on that interval. Okay? So we have one down. Now the next one, we got to pick something between negative root 3 and negative 1. You might say, oh no, I don't have a calculator, how can I do this? Not too bad, just remember, square root of 1 is 1, right? Square root of 3 is a number between 1 and 2. Well, let's pick a square root number that's in between there. Let's go negative square root of 2. Right? We know for a fact that that has to be in that interval, right? Because it's in between the negative square root of 1 and in between the negative square root of 3. So now plugging that in. When we plug in negative square root of 2, well, if you have a negative and you subtract off another negative value, you're going to get a negative. So that's just a negative there. Now, negative square root of 2 plus 1, that might be tricky for some of us, but remember, this is just the square root of 1. And if you have the square root of 2, that's negative, and then you add 1, that means this whole thing has to be negative. So negative times a negative makes a positive. And notice, once again, we don't have to check the denominator because we're squaring the whole thing. So that means it's going to turn positive down below. So we have, it's increasing also on the interval negative square root of 3 to negative 1. Okay? So we have increasing from negative infinity to negative root 3, and then union with this for the increasing portion. But we don't care about that, we're caring about decreasing. So next interval, negative 1 to 0. Let's pick a number in between. Let's go with negative 1/2. Didn't have to be negative 1/2. You can choose any old number. Remember, the denominator is going to be positive. So we look in the numerator, you go negative minus that 1, you're going to get a negative value right there. If you go negative 1/2 plus 1, oh boy, that has a plus here. So notice, we finally have our first negative. So this is decreasing. On our interval from, first off, negative 1 to 0. We'll see if there's any more now. Okay. Next interval, 0 to 1. Okay. Oh, I'm sorry. When I wrote this, I did make a minor error. I wrote on the negative root 3, the root 3, and the 0 that it was a 1. Those are DNE situations. Does not exist. My apologies. So does not exist, does not exist, does not exist, does not exist. Okay? So you have situations where it does not exist. So something to keep in mind there. And if we go forward from here, let's look at that next interval. From 0 to 1, let's pick a number in here. So in this interval, we have a 1/2. When you go 1/2 minus 1, you get a negative. 1/2 plus 1, you get a positive. So negative times positive makes it negative. So we can toss in this union of 0 to 1. Moving forward to the next one, between 1 and square root of 3, we'll take the square root of 2. Now, square root of 2 is larger than 1, so we'll have that be a positive, and this is a positive. So now we have positives. And for our last interval, you can pick, once again, you can go 10, you can go 4, whatever you really choose. You plug that in and you get positive and another positive. So you have increasing on that interval. So really the only interval where we're actually decreasing is from negative 1 essentially to 1. Right, because that 0 is the only point in between where it's not defined. Doesn't mean it can't be increasing along the way though. So you have negative 1 to positive 1, or negative 1, 0, that open interval union 0, 1. That's where we have this function to be decreasing on. So hopefully that makes sense. That's coming up. You're going to be dealing with the critical points if you haven't already. So hopefully that gives you a little preview as to what's coming ahead. Sooner or later we're going to take that information and start graphing all this stuff. So I hope all that worked out, and post some questions if you have them in the meantime, and I'll try and answer them the next time I do a live session. Okay? Have a great night.